Select the best set of reagents to accomplish the following transformation. So if we look at our starting material, we should notice that this is an alkane. So alkanes are really the unfunctional group. There are not very many reactions that alkanes can do. So alkanes can undergo combustion reactions. So these are reactions similar to burning gasoline as a fuel. And the product of that combustion would be CO2, carbon dioxide, and water. So if we want to keep our carbons attached to each other and not completely break this down, that's not the reaction that we're looking for. So the only other reaction we see of alkanes that we can do is a radical halogenation. So when you have an alkane as a starting material, for sure, your first step needs to be a radical halogenation. And so the reaction conditions for that would be your molecular halogen and something that can start a radical reaction. So heat or light or sometimes a peroxide. Okay. And the halogen that you're going to see most often used for these reactions is bromine. So this is usually Br2. And this is because the bromine radical is kind of the right combination of reactive enough but not too reactive that allows us to somewhat control this reaction. And by control, we mean by where that bromine adds. So the bromine will add to the carbon atom where it can form the most stable radical. So if we look at the alkane that we're starting with, all of these carbon atoms of the ring, except for where the methyl group is, those are all secondary carbons. This is a tertiary carbon, and we have a primary carbon. Radical stability is the same, follows the same trends as carbocation stabilities. So we are most likely to form the tertiary radical, which means that after we do this radical halogenation, we will be adding the bromine to that tertiary carbon. So now that we've done this, right, what we're doing is we wanted to put some sort of handle for functionalization on this alkane. Because without a functional group, it's hard to do any sort of reactions. So we've now transformed it into an alkyl halide. Right? So radical halogenation will do this, and it'll put that, usually we use bromine, and it'll put the bromine where it can form the most stable radical as an intermediate. So that means it's going to select for a tertiary carbon over a secondary or primary. And then we need to transform this to our final product. So we should notice that although the product is a bromide as well, it's not the same alkyl bromide that we formed from this radical halogenation. But what we should notice is that the carbon atoms that hold the bromine are adjacent to each other. So what that tells us is the likely intermediate to go between these two structures is where we have a pi bond between the carbon that has this bromine and this one. So we need to do an elimination reaction. So this alkene is our likely intermediate. So when we do an elimination to get to this alkene, we have hydrogens on the N methyl group, and these are the ones that we actually want to eliminate to get to this alkene. And we also have hydrogens inside the ring. So if we were able to take a hydrogen from inside the ring, we would form a more substituted alkene. So that would be the natural pathway for an E2 to give you the more stable alkene. To force this elimination kind of to the outside of the molecule to do the E2 reaction and give you the less substituted alkene, you want to use a bulky base. So something on the line, along the lines of tert butoxide. So you're going to use that bulky base to form the less substituted alkene. And so this base can take one of these hydrogens from the methyl group. The electrons from the carbon-hydrogen bond come in to form your alkene, and then you're going to push off the bromine. And then from this alkene to the product, what we need to do is we need to add a hydrogen. So you can see a hydrogen is being added to this alkene carbon, and a bromine is being added to the end alkene carbon. So we need to add HBr, but we need to do this in a way that is an anti-Markovnikov addition, because we want the hydrogen adding to the more substituted carbon, and we want the bromine adding to the less substituted carbon. So the way to have an anti-Markovnikov addition of HBr is if we have peroxide present in there. So these are the conditions for the anti-Markovnikov addition of HBr. So we are looking to do first a radical bromination. So this is the first step we want. So first we're looking to add Br2 and something like heat or light to initiate that radical reaction. Then we want to do the elimination with a bulky base. And then finally, we want to add HBr in an anti-Markovnikov fashion, so we make sure we have peroxide. And so we see that these conditions are what is shown in option D.